Okay, cool. The goal of this talk is to show how you can use Akka Streams to compose stream processing, compose different stream processing components. And I have not gotten my water before that. Well, right. Goal of this talk is to show how to use Akka Streams to take messages received via WebSocket from WebSocket connections to a server and publish them to Kafka. But before we start, let's go a quick overview of Akka Streams, right? I won't be getting into the details of Akka Streams, how to use it, how to use the different features. This is more of a talk designed to motivate you to go out and learn about Akka Streams by showing how you can use it to compose, well, more or less anything stream processing related. So a few examples here, right? It's like Legos for stream processing. I just came up with that today. It may or may not work. Right, so you can take Kafka, you can stream messages to or from Kafka, you can stream messages to or from a WebSocket connection, you can do high-level network I/O, you can have streams of HTTP requests to HTTP responses, you can define a server that way. You can do low-level network I/O, you can send streams of messages directly over TCP between servers if you need to, like if you need to skip the overhead of using HTTP itself. Some people do. You can use files, local on S3, pretty much in the same way. You can stream bytes to and from them. And if you can connect all of these things to the input or output streams of processes. So if you wanted to stream a file from S3 into the input stream of a process and then stream the output stream of the process to another file in S3, you can do that really easily. That's not what this talk is about, but it's really important to just sort of hammer home that you can use it as Legos for stream processing. So our goal tonight, this is quite small. Let's see if I can, I'm trying out a new presentation framework. So can everyone read that part at the bottom? Can some people read that part at the bottom? Yeah. All right. Sorry, Right, so what we're doing tonight, we're creating a server, it'll consume events via WebSocket, and it'll publish all of them to a single Kafka topic. So at that point, you can do whatever. You can use that as input to Spark, to whatever your big data, real-time data analysis platform of your choice is. You can just read from that. You can basically use it with anything. Kafka is a very good glue for different systems in a microservice architecture. So in case you can't read that bottom line, that's the case class that we'll be working with. It's an event, there's a client ID, there's a timestamp, there's nothing else. It's pretty clearly meant as a placeholder. You could put messages there, you could put whatever data really that you wish to collect from the front end. So we'll be working with that event case class for the rest of tonight. And there's a bit of boilerplate here that you really don't need to read all of. Basically, what this is on the companion object of event. First, very simple, you have the JSON serialization and deserialization via format. That's via play.json. It just uses macros to create some implicit classes that'll convert instances of event to and from JSON. And then here you have a slightly more verbose serializer and deserializer used for Kafka. All these really do, the serializer turns events into bytes, the deserializer turns bytes into events. We'll be using those to publish from, or publish to and read from Kafka later in this talk. So, as always, there's boilerplate, right? Implicit boilerplate. First, an actor system. That's, as from the talk before, it's an Akka actor system. It provides actors as a unit to run computation in a distributed environment. They communicate via message passing. Then there's an execution context. That's just the system dispatcher that'll be used for mapping over futures and registering callbacks in futures. Finally, there's the Materializer. So that just uses the actor system, the implicit actor system, to turn basically blueprints in Akka Streams representing stream processing graphs into running instances of those stream processing graphs using actors created by the actor system. That'll all be in the background, but if something looks like magic, it's important to remember there's a lot of implicit, more heavyweight stuff that it's running on, and that's what that is. Right, so let's zoom out a little bit.
Could you repeat what Materializer is, please?
Right, sorry. The Materializer, it takes a description of a stream processing graph that's a series of nodes that communicate with each other via streams, right? That stream data from node A to node B. And it turns that into a running instance of that graph created using actors. By analogy, it's like an execution context. As an execution context is for futures, Materializer is for Akka Streams. You don't need to understand the details of it. It's just something that needs to be in the implicit scope for most of the stuff to work. I'd be happy to discuss it more later. But if you're willing to accept that it's magic, and then let me show you how you can use the magic to build cool stuff very concisely, the idea is that that'll motivate you to learn more about it. But I'll definitely have time to answer questions after. And during, too, of course. But so this is getting started, right? And most of these parts of this talk will, as down there, have these little ASCII art diagrams. And those are showing different components of the stream processing graph that we're building, right? So this code, it creates this, a stream processing graph component that consumes events, right? That's the arrow going into it. It consumes a stream of events and publishes them to Kafka. So the specifics of how we create that, first we use reactive Kafka. It's a library that uses Akka Streams to communicate with Kafka, or reactive streams rather, which is the standard that Akka Streams is built on. We have our Kafka instance. It's running on Docker machine locally. That's just hard-coded because I can. And we use that to create a sink. So what that is something that consumes a single stream of messages of type event. And when we run it, it doesn't, the side effect of running it is unit, right? So it produces an instance of type unit, aka void, aka nothing. We can ignore that for now. So what we're doing is first we're creating a flow that just does nothing, right? It's the identity flow. It's from event to event. Then we're mapping over that. We're wrapping every event in a producer message. Finally, we're sending that to a sink that we create using the Kafka client and some properties that we pass in, right? So there's the IP of and port of the local Kafka instance. There's the topic name. That's the topic that we'll be publishing to. And then there's the serializer that we created in this giant glob of serialized, deserialized boilerplate. All the serializer really does is take events, turn them into bytes. Those bytes are then published to Kafka, which is a distributed log framework, or log service. So at the end of that, though, what we've created or defined is a blueprint for a stage in our stream processing graph that takes events and publishes them to Kafka. We'll have a number of these ASCII art diagrams. They're designed to be composed, right? So if we have another source of events, we can just sort of plug that together with this sink without needing to know every detail of how the sink is implemented. That's really the key to the whole compositionality of it, the whole Legos approach, right? So what we're going to do now, and this is a bit hacky to be honest, we're going to use a source queue to create a single running stream that multiple streams can publish to. For every WebSocket connection, we'll be getting a stream of WebSocket messages. Those will all be publishing to this source queue, which will be connected to the Kafka stream, or Kafka sink. So a source queue, right? It's very simple trait. It's just something that you can offer an element to. It'll either reply with a future false if it's not able to accept that because its queue buffer has been overrun, or a future of true if it accepts that. So right here, we create a runnable graph by combining our source, or queue source, right, given 1024 as the buffer size, and an overflow strategy that we can gloss over for now. And we're combining that with the .to with the Kafka sink that we created on the last page. So you can see here, right, it's a sink that takes events, and this is a source that creates events. So we combine them. Now there are no hanging inputs or outputs. That's just a runnable graph that we can create. Everyone with me so far? All right, cool. So then we run the runnable graph, right? And we get a source queue as the output of running it. So it's a runnable graph of type source queue of event. That means that when this blueprint, right, this graph is just a blueprint, defining it hasn't actually caused much computation to occur. When we run it, we get a source queue of events. That's how you can get things out of materializing a graph, like futures if you have, anyway, if you're folding over a stream, for example. So now we have our source queue because we have actually run it using the materializer we defined earlier. And here's the shape of the stream processing graph we just created, right? So events go from the source queue to Kafka, and we can just use the source queue to in-queue events and to be sent to Kafka. So now we need to actually write to that queue, right? So what we do here, we define a queue writer, abstract in terms of type T because we can. And all that does, it takes a source queue of type T, creates an identity flow using flow of T, uses map async to offer elements to the queue, and then sync.forEach to just run like a function on the result of every offering, right? So if it's false, that means that it was unable to give in queue element on the queue, and it uses print line to just log an error. And if it's true, we do nothing because that means the message got onto the queue. Yay, we've succeeded. So in this case, it's an element of type T that's sent to a source queue of type T. And the source queue provided from outside when you're creating the graph stage. Right. So now we have our stream of messages to Kafka. We want to start dealing with stuff from the WebSocket, right? We're going to open a lot of WebSocket connections in the near future. So first, we want to parse the messages. So we have a flow from messages to events that takes just text messages and parses them as JSON and attempts to transform that JSON into an event. And we'll throw an exception if that fails, because this isn't production code and we can do stuff like that. So this flow, right, it's just a component. It's a sort of equivalent to a function. Not really, but you can think of composing flows as function composition, in that you have a flow from message to event, you have a function from message to event. The flow runs over multiple elements, the function would run over a single element. They're conceptually equivalent, but not implementation-wise. So we've defined this other component. Let's get a bit more complicated, right? So we're going to bolt that onto parse messages onto the queue writer. So all that does is it parses messages that are coming in from somewhere. It writes those messages to the queue via queue writer. And then that is right here. Well, I can't select just part of a line, so it doesn't really work. But right here, anyway, everyone wave your hands around. Right here, that's a sink. So that's a sink that consumes messages. And source.maybe is a source that may or may not produce a single element. Here, we're not going to produce anything. We just have this here so that the WebSocket connection doesn't close. We need to keep that promise of a potential element there. So then we combine the two, flow.fromSync and source, right, as up here. We take a sink and a source that perhaps aren't related at all. We combine them. The source is the input of the flow. The sink is the output, right? This is what we're going to handle every WebSocket connection with. Every WebSocket connection is a flow from message to message. Messages consumed by that flow are sent from the web page via the WebSocket connection to the server. Messages produced by that flow, here in this case we don't have any, but we don't need to tell the compiler that, will be sent back down the WebSocket connection to the web page. Right. So now we're going to have a flow from HTTP request to response, because we're going to have multiple WebSocket connections, right? This isn't an interesting talk if there's only one WebSocket connection open at a time. So we're using a bit of basically magic from Akka HTTP to define a routing DSL, domain-specific language. So what this is doing, if we get a GET request with that being the end of the path, we'll just serve up test.html from the local resources file. If we get a GET request to /ws WebSocket, we will handle that WebSocket message with the flow that we created earlier, right here. So every message will be parsed and then sent to the source queue to be sent via Kafka. And then we'll just not send anything down the pipe because we don't need to. Right. So now we run that using Akka HTTP. What we're doing here is saying we want to handle every request to port 9000 on localhost with this routes flow, right? This flow from request to response. That, like, at a really basic level, that's what like a server is, right? It takes HTTP requests and yields HTTP responses. And you probably had it explained to you that way in some basic class, but then you can't really implement a server as an actual flow. There's a bunch of other stuff you have to do. But with Akka Streams, you kind of can. Simple example that this is. You can see down here, there's a ASCII art drawing of the routes flow. So finally, test.html, right? I didn't actually introduce that. I'm not good at JavaScript, I'm not good at HTML. This is a very simple page. All it does is generate a random client ID, open a WebSocket connection to localhost /9000 WS, and then log to console everything that happens with that. And finally, every second, every 1,000 milliseconds, it sends a event with a client ID and a timestamp to that WebSocket and logs it to the console. So Finally, because we want to actually see that stuff actually goes onto Kafka, we're going to listen to Kafka with a consumer. So all this does, it consumes messages from Kafka, same local Kafka instance, same topic, events. It also has a group ID, right? If you have multiple groups, they'll each consume every message. But if two consumers of the same group ID, they'll only see each message once. That's really useful if you want to parallelize, handle something with multiple instances reading from Kafka. And we just then map over it to unwrap the wrapper that's all our messages have, just get the value. Finally, we run it with run for each. What that does is it just creates a sink that runs a function using for each on every element consumed by it. So you can see the shape of the graph down there, right? Starts with Kafka, takes events, over to sync.forEach, and then runs println on each of them. So let's go to the actual presentation, or the actual demo. So we already have some messages on Kafka from when I was testing this earlier. So you can see what that looks like. So right here, stop presentation mode. I'm going to open up a bunch of local instances. So each of these is going to publish an event with just its client ID and timestamp once every second. And you can see that in the console log. Nothing in the UI because I'm a backend developer and I don't do UIs. So yeah, you can see here every second, different client ID per service, different timestamp. And over here, we've got our server running, listening to Kafka. So every message here is something that's been published to Kafka by our server and then read back from it. And you can see that these have a bunch of different IDs just mixed together. Now let's just throw out like a more ridiculous amount of these because we can. Right, so still publishing. We haven't dropped any elements. I haven't tested this with like an actual reasonable web scale number of like 10,000 clients or something, only because I don't know any libraries for like simulating a ridiculous, obscene number of WebSocket requests at the same time. But if anyone has anything they recommend later, I'd appreciate that. So that's basically it. You can see the entire example here. It's in 88 lines, not including the HTML page, including the imports. So let's recap what we did, right? We created a persistent stream to Kafka via which we have a source queue that we can just getting with a function that returns future of Boolean and queue messages. We created a server via a flow from request to response, and then used another flow to handle every WebSocket messages via a single route there. And then we created another consumer for Kafka to log all those messages in really just like a tiny amount of lines. I've implemented things that do like a fraction of this that have taken like 3 or 4 times as much code. Of course, every line of code is another opportunity for bugs. Bugs are roughly proportional to lines of code, so anything you can do to make things more concise, assuming it doesn't make everything else worse, like some of the stuff I've done with Scala Z, even though it's really fun. Sorry, didn't mean to, anyway. Yeah, so it's really concise. You can do a lot with it. You can glue a lot of different things together. Any questions? I guess not. Oh.
Could you explain a little bit like what happens behind the scenes to keep like the WebSocket open? So because the requester is just creates the WebSocket, and then I think you mentioned it with the maybe or something. How is that magic?
Oh, great question, right? So,
Can you repeat the question, by the way?
Sorry. What happens behind the scenes to keep the WebSocket open? Let's go back to the example for a second, or the page with that for a second. So source.maybe here, right? If this was a source that just instantly closed, it would instantly close the WebSocket connection, right? What this does, source.maybe, let me actually show you it from a Scala standpoint, is a source that materializes to a promise. So when you create it, it just like spits out a promise. And if you complete that promise with something, it'll emit that and then finish. If you complete that promise with none, it'll just close. If you never complete that promise, if you just leave it hanging, it'll just always be open and like not actually completing. So that's what source.maybe does. It's just sort of there to not complete, because we really want to treat the WebSocket as a sink that just consumes elements, but sort of by like the nature of the WebSocket protocol, it wants to both consume and produce elements. And we have to give it something to consume that doesn't close instantly, and that's what maybe is used for. Does that answer your question?
Yeah.
Awesome. Anyone else?
Just kind of curious why you chose to use WebSockets from the browser when it's, like we're saying, it's really just kind of one-way communication from the browser to the server.
WebSockets are cool. Next question. Or sorry, you asked why I chose to use WebSocket. So when it's a one-directional communication, when I could perhaps use like.
When this example is one-directional.
Oh, totally. You could really just like post every time something happens, but. I don't know. I mean, is it actually beneficial if you want to publish events on a regular basis to use WebSockets instead of like HTTP post? I actually don't know. I just jumped to WebSockets because they're cool and I wanted to do a demo, but that's actually a very good question.
How was Spray?
Spray? Mm-hmm. I think Akka HTTP and Spray are sort of converging, right? Like,
Interoperate.
yeah, so as I understand it, Play and Akka HTTP are sort of going to be merged. If you want like a WebSocket connection in Play, you'll be using Akka HTTP in the next version or two, theoretically. But yeah, Spray and like I believe the routing DSL used here, which is the Akka HTTP routing DSL, is originally from Spray, right?
Yeah.
So it should be familiar if you're familiar with Spray. Cool. I think that's it. If anyone has any other questions, find me after.